Then we do the same thing for the Meteor. In every frame of the video or in every for every dot that can be determined to belong to the Meteor, we can do just the same, determine its position and its magnitude. Next, we are able to identify the stars with the help of some catalog. After this is done, if they are identified correctly, we should be able to compute a correction that is valid, at least locally, at the position of the Meteor itself, and finally apply it to the position that is measured. The common coarse solution to this problem is a parametric method. We will be trying to fit some sort of projection, which is basically mapping from X and Y, the coordinates on the sensor. By use of some black magic, we try to transform this into the zenith distance of the meteor or the star and its azimuth in the sky. One very good solution, probably the simplest complete one, is the Bogovička projection, which is also fully invertible, which means we can go also the other way around, at least for the values of parameters that are useful for an actual optical system. This also means we can test it very well, but projecting forward and backward, and we are also able to split the whole thing into several steps, which are not very important. As for the catalog, there are many of them available on the internet, so feel free to download whatever you like. For us, it is a simple text file with tab-separated values where we have equatorial coordinates of all the stars and their magnitudes. When this is finally gathered in our computer, we can let the library AstroPy sort it out. We can transform everything to local coordinates at the position of the observer at the correct time, include all sorts of effects. And optionally, we can also include planets because we see them in our videos. Again, AstroPy takes care of basically everything. When the software is finally built, it might look like this. So now I know that showing a piece of software with screenshots is probably not the sexiest way how to do it, but if I were to run it really here, I'm pretty sure it would crash in a way that no program has ever crashed in before. So this is our sensor view. We can see the stars, we can see the meteor up there. And for the catalog, not much of an adventure, simply a bunch of stars somewhere in the sky, but at the correct positions already. The method of parameter fitting is very easy. We're trying to minimize some parametric function with 12 parameters in case of Bogovička's projection. And we are trying to find, well, this horrible thing on the right just says that we are trying to minimize the square of the distances from every dot on our sensor to the nearest star in the catalog. We're using the basic null-deriving method from the SciPy library. We've written a class called matchmaker that simply matches every dot to a star and does this naively. For every pair, it just computes the distance, takes the minimum. When we do this, we can picture this. It's not very good here on the projector, but you can still see some yellow and red dots. So the yellow ones are already very well matched, and the red ones, for instance, here, are not so well matched. And after some massaging of the parameters, which is probably fairly quick on today's computers, we obtain a solution that is globally valid, of course, not perfect, and also apply this to the meteor. So the meteor, you can see, has shifted a tiny little bit. Of course, this is not as fast as we would like it to be. So the problem is that many stars from the catalog, as you can see here, many of them were not seen. So we are able to cull them, remove everything that is far from a dot, remove everything that is too faint. And when this is done, we are trying to do something smart. We pair every dot to a star, make it fixed. This is called in a class that is called counselor. First we made matches, now we're counseling the couples. And from now on, all the operations are a linear time because you don't have to worry about the pairs or anything. Everything just works in the number of meteors, which is very, very fast. Again, we optimize and optimize and optimize and massage the whole data set, and we're left with this. A bunch of parameters on the left and a nice visualization in the middle. Usually people stopped here and said that, okay, I applied this projection to the meteor and whatever the solution is, I use it for further calculations. If I have two observations from two different stations, I can find the true position and so on. We're going further. This was the core solution. The fine solution is by the kernel smoothing correction, which is, again, fairly easy, not trivial. The basic premise here is that even the optimal solution of the project still has some systematic errors. For instance, with AMOS, with our network of cameras, the optical system is much more complex than is assumed in Bogovička projection. There are thermal stresses in the physical components. There are manufacturing defects, many more. So we try to have a look at what happens if we plot the errors as they are shown here. So this is a vector plot over the entire projection of the sky on the unit disk, and we see that something's happening, and it's not completely random. It's not just noise. There's a systematic errors. After some more massaging, we arrive at another solution. This is global minimum of the Borovichka projection we are able to find. And in the yellow stars, the yellow arrows are the stars, and the green arrows in the back are somewhat smoothened form of the entire thing. Again, we can plot the errors not against the background, but against other parameters such as the zenith distance. So here we see that, okay, this is not very systematic. It's mostly random. In azimuth, we expect it to be also pretty uniform. The smoothing itself is, again, easy. At every point of the unit disk, we just compute a weighted average of all the referenced observations with the vote strength of every star that has a fixed position and the observed position is somehow decreasing with the distance from it, which we denote k. And in the bottom, we just see a weighted average based on the distance. Very easy. The correction assumes or has several assumptions. First of all, that the field deformation is tiny, which is probably true because we saw that the stars are already at their positions. That there are no high frequency components, which is in case of hundreds of stars, which is usually very well fulfilled as well. But of course, the problem is sometimes it happens that we don't have sufficient star coverage. For instance, there is a cloud in one half of the sky, and if the meteor is not passing exactly among the stars, then it's not very easy. The good thing about this method is that it's not very sensitive to single incorrectly identified stars. So if there is 1 or 2 or 5, it's not much of a problem unless the meteor is passing exactly through it. But then again, you see it, so you can correct for it. As for the kernel, which I mentioned, this is just a window function. As for its shape, we have very much freedom, probably too much freedom, because it turns out it's not very important which of the functions we use. As long as it's generally hill-shaped, it just works. What is very crucial is the bandwidth or the scaling factor, the width of the function. Usually we start with fixed bandwidths, again, set manually by trial and error, but we can also use some more advanced methods such as the k nearest neighbor in the sky and so on. If we use a bandwidth that is too narrow, we arrive at what is essentially the nearest neighbor algorithm, which you can see, for instance, in the bottom right, that the entire area is just shifted by the same shift as the nearest stars there. If we use something more wider, it gets smoother and smoother. And beyond that, if we overdo this, suddenly we arrive at something that is probably too smooth, and you can see just that it's pinched in one direction and stretched in the other one. So probably this is not good either. This can be always expanded into the base of Zernike polynomials. For instance, the one we saw here. You can see the pinch and the stretch is the V2 minus 2 in the top. So we also always expect that there will be only a few of these components. The same procedure is applied to magnitudes, which are scalar values, which means it's simpler. The nice thing about this algorithm is that it automatically accounts for everything, extinction, vignetting, whatever. Well, in theory, at least, if we have a very good star coverage, then it can be done. In reality, it's not that perfect. And there is always the problem of pixel dwell time, that the stars are stationary in the sky and the meteor is not. So there has to be an extra correction. Again, we can plot this in our software as well with a nice 3-color plot. Again, we see the correction for the meteor and the stars. Or in the unit disk, it looks like this. Something has to be amplified a bit and something has to be suppressed. Finally, the holy grail of the entire effort is to write this into a command line interface program that will just run automatically in batch mode. We strive for fully automated pipeline processing, where we would identify everything, cull the stars from the projection or from the catalog, minimize everything, compute the correction, apply it, save it. Quickly, we got a dose of reality pills that probably this is not possible to do fully automatically because it still requires a lot of manual preparation. For every observation run, this needs to be done at least once. We identify everything manually and save the constants for the station, or, well, after any service task, or, well, if it's moved a bit, it has to be done again. I'm able to do this within 5 minutes, or one of my colleagues who was so lucky to be able to toy with this, they can do it in a few minutes. And then the program automatically for each file can just load this coarse projection solution and run the entire algorithm, remove the stars, pair the dots to the stars, compute the solution, apply it, and save it to the file, which is fairly nice. Now, I know that probably you haven't seen much, because I really hate showing programs real time, and there is not enough time for this. But if you'd like to see how it actually works, feel free to talk to me, hunt me down somewhere during dinner, after dinner, or if you're very brave, visit my GitHub page directly. It should be, at least in theory, possible to download the whole thing. It's Python, so you don't need to build anything. Just run it from the virtual environment and toy with it if you feel like this. That would be it.